Alright, we're back, this time with divergence theorem. Um, if you have not watched the video about the nabla operator, the gradient, the divergence and the curl, I recommend watching that first because it's a very important, the divergence is very important to understand in this context. So with Stokes' theorem, what we saw, and Green's theorem, was that we could take some sort of a surface curl integral, and we could relate it to a vector line integral because things canceled out inside. Similarly, this, instead of relating a surface to a line, we're going to be relating a volume to a surface. And so how we're going to do that is I want you to imagine we have a sphere, and this little blue box is a small infinitesimal dV. It's a small bit of volume. And what I've done here to make it easier for me to draw is I've drawn a cross-sectional view as if you had cleaved through this, and you're seeing all the little infinitesimal dVs in there. Now, if you'll recall with divergence, divergence is the measure of how much goes into a volume versus how much goes out. If the same amount goes in that goes out of a volume, that is zero divergence. If more goes out than comes in, that's positive divergence. And if more goes in than goes out, that's a negative divergence. The way I like to think about it is if you're pumping a lot of water into a river and less is coming out, then that means that something's stopping, impeding the water, so that's negative. Whereas if more is coming out than is going in on one side, that would mean that you're probably pumping it. Well, water is incompressible, so that's a bad analogy, because technically the divergence of water is pretty much always zero. But I think you get the point. So what we're doing here is we take, I'm just taking a look at a couple of sources and sinks. With a vector field, we call sources where there is large positive divergence, a bunch of arrows going out, and sinks is where there's a large negative divergence, or a bunch of arrows going in. So here I have a source drawn, here I have a source drawn. But the point of this is to illustrate what all of the vector field looks like. Imagine filling in arrows everywhere in this surface, or in this volume. So anyways, the point of divergence theorem is that if you have a source inside of the volume, you'll notice it'll have field lines, vector lines. And you'll notice that the vector lines will pass through a bunch of these little chunks of volume. And then at some point they'll exit the surface. Whereas if the source is outside of the volume, every single vector line that goes in also goes out. So in other words, it comes in here, it leaves there, it comes in here, it leaves there. So really that doesn't actually add to the amount of flux on the shape, and that's kind of goes to Gauss's law. But anyways, if we look at the divergence of a cube, let's take a look at the divergence of this little dV here. So these are all different infinitesimal volumes next to each other, stacked in order. And so if we have a field line starting here, you will notice that the field line leaves this dV, we'll call it dV1. It leaves dV1 and goes into dV2. It then leaves dV2 and goes into dV3. And so if we're actually looking, because what we're looking for here is what is the divergence total across the whole shape. And we're doing that by adding what the divergence is on every little infinitesimal volume and summing it using integration. So if we're looking to figure out what is the divergence of the whole volume, when you zoom in, you'll notice this is a pretty cool trick. I know I wouldn't have thought of it myself. But remember, when an arrow leaves, that's going to be positive divergence. When an arrow comes in, that's going to be negative divergence. So you'll notice that when this arrow leaves dV1, that counts as positive divergence. So that line is giving positive divergence. But then the line enters dV2. Well, entering is a negative divergence. But then it leaves dV2, which is a positive divergence, but then it enters dV3, which is a negative divergence. but then it exits dv3, which is a positive divergence, but then it enters dv4, exits dv4, enters dv5, exits dv5, and you'll notice that we get all the way to dv6, and it enters dv6, which is going to be negative divergence, and then it exits dv6, which is going to be positive divergence. So if we go ahead and cancel out the signs that cancel, because this line being positive leaving here and going into here being negative, those are going to cancel. These are going to cancel at the intersection surface. These are going to cancel. Those are going to cancel, and those are going to cancel. And what you'll notice is we're left with one lone sign. This guy right here. It's a positive sign in this case. And so the fascinating thing about the divergence of a volume is that if you want to know the divergence of the volume, what happens on the inside doesn't actually matter. You can write it in a simpler way using only what happens at the surface, because anything that enters the volume will indeed leave the volume. That'll cancel out the divergence. Anything that starts in the middle will cancel out divergences between each volume until it gets to the surface, and then there will be some amount of divergence that we can calculate from the surface. Well, it turns out that if you're trying to figure out field lines, vector field lines that go through a surface, we've done that already. It's called a flux integral, a surface flux integral. And so we remember the flux integral for a surface looks like this. You take the vector field line, dot it with the normal of the surface, and then integrate all such infinitesimal surfaces. And in this case, of course, we're looking at a volume, so it's a closed surface. Well, we've just now proven that all that the divergence is of a volume, the entire divergence of an enclosed volume, is exactly equal to the flux through the surface of that volume. And so this right here is divergence theorem. This and Stokes' theorem are powerful tools, because sometimes you might have an integral that looks like this that is really difficult. But then you can convert over here, and maybe it'll be simpler to solve. And for those of you in electrostatics this semester, Physics 212, you have seen these in action. Stokes' divergence theorem, they pop up a lot in the Maxwell equations. So I hope this video helped. I know when I finally figured out what this law even meant, I was very satisfied. So I hope this will help you as well.